Chapter 8, the quantum mechanical model of the atom. This is one of my favorite quotes from Niels Bohr. Anyone who is not shocked by quantum mechanics has not understood it. Let's see if we can get rid of that. There we go. So the beginning of quantum mechanics. Until the beginning of the 20th century, the 1900s, it was believed that all physical phenomena were deterministic, meaning you can look at what a piece of matter is doing right now, and you can predict what it's going to do in the future based on that. But there were many famous physicists that discovered that this is not true for subatomic particles, particles that are smaller than an atom. The present condition does not determine the future condition. This does not make sense in our human experience. So what this means is if you shoot an electron down a path and measure where it lands, and you send a second electron down that path in exactly the same way, it's not going to land in the same spot. It's going to go somewhere else. And that doesn't make any sense, does it? Because that's not what happens with baseballs or arrows or anything large enough to see. If you do the same thing to something, the same thing's supposed to happen. But that doesn't happen with the very small. So the absolutely small, or the quantum world, this is the size of an electron, right? Very, very small. They're so small that they behave completely differently. They've got different rules. So when unobserved, absolutely small particles like electrons can be in two different states at the same time. And that's not physical states, like you could stand on the border of, Nevada and California and be in two states. Right? No, two different states. So an example of this is a radioactive nucleus that's not being observed can be simultaneously emitting a particle and not emitting a particle. We'll learn that an electron can be a particle and a wave at the same time. You should find this confusing and disturbing, because it is. So how small are electrons? They are incredibly small. A single speck of dust, which is something that you just could barely see, right, has more electrons in it than the number of people who have ever lived on Earth. Right? That's a lot of electrons. So small. I mean, you just can't even get your mind around how small these things are. The behavior of the electrons determines a lot of the behavior of the atoms, but electrons are too small to observe in an atom. We can barely get those really fuzzy pictures with a scanning electron microscope of an atom. Looking at the electrons inside, which are like mind-bogglingly smaller, just not possible. The other crazy thing about electrons is that if you observe them in any way, you change their behavior. That just doesn't make any sense, because how does the electron know that we're looking at it, right? How does it know? It doesn't make sense. But that's what happens with the very small. So you've probably heard of Schrödinger's cat. This is a thought experiment. No cats were harmed. And it illustrates how quantum strangeness, how the quantum world works, does not transfer to the macroscopic world that we can see. It just doesn't make any sense. So I've got a couple of different videos here.
I need to find the best way to learn math and science.
This wouldn't be a YouTube channel without a cat video. So without further ado, we present Schrödinger's cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute, and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment. And it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I has answer, please?
So that's a cool channel called Minute Physics. And then here's another one. This is from a site called I Don't Think It Means What You Think It Means.
Hello and welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrödinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrödinger, who helped piece physics back together after Einstein and his crew blew a giant freaking hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics, where you could observe objects moving and predict how they react to various forces. But then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. Think to say, what now? My friends, I shall now introduce you to one of the biggest mind flogs of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrödinger came up with this thought experiment to help everybody understand it. Say you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me here. I'll say that there's a 50-50 chance that one of the radioactives is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrödinger? This is not the best way to get people behind the idea of funding the sciences. So there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead, and an equally good chance that the vial hasn't been broken and the cat's just kicking it, wondering what's for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time. Because that's how quantum objects act. So then, that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws. So it, just like every other cat in history, is either alive or dead. Schrödinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom has decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrödinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrödinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. And alternatively, the point is that the universe is pretty freaking weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, and at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive, and one in which the cat is dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think it's such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below, and I'll, do my best. Also, if you have an idea for I don't think that means what you think it means, please let us know about that too.
Yeah.
If they can't see electrons, how do they know about any of this? Are they just guessing?
Yeah, so if we can't see electrons, how do we know about any of this? Or are we just guessing? That's a great question, right? We can't observe them directly, but we can observe the effects that they have on other things. So, can you see the wind? No. Can you see what the wind does? Yeah. You can feel it. You can see it, pushed a tree over, right? So, just because something cannot be observed does not mean it doesn't exist. And that's, I think, one of the things that scientists see as a challenge. How can we learn about these things that we can't see? And so then there's this problem solving and this cleverness that's needed to figure out how can we observe these things? Great question. Anybody else? So, like Niels Bohr, this is the same quote at the beginning. Anyone who's not shocked by quantum mechanics has not understood it. Schrödinger, who's one of the guys that developed this, wrote, "I don't like it, and I'm sorry I ever had anything to do with it." Albert Einstein, you've heard of him, attempted unsuccessfully to disprove quantum mechanics until he died, because he didn't like it either. It's not a comfortable concept, but nobody can disprove it, so we're kind of stuck with it. So this quantum mechanical model explains how electrons exist and how they behave in atoms. And it helps us to understand and predict properties of atoms that are directly related to the behavior of electrons. And so this is things like, why are some elements metals and others are nonmetals? Why do some elements gain one electron when they make an anion, and why do some gain two? Why are some elements extremely reactive and others don't react at all? And this also explains a lot of other periodic properties that we observe in the elements.